Now, the question is the descent algorithm I showed you, that was a very simple function. It was dependent upon like maybe just one variable. So it's easy. You can just compute derivative of that function with respect to that variable. But the neural networks are a little more complicated, right? It's not just one variable and one function. It is actually chain of functions. So if we start with the first layer, if you treat that as a function, then input to that function is your input image, let's say, or whatever input data point you have. And again, that's going to give you some output. So that output is again going to be input for your next layer. So if you treat like each of these layers as functions, so essentially it's like a chain of functions, right? Where output of one of the function is actually input to the next function. And eventually, like at the end, the output of the network is actually going to the loss function as input. And for loss function, you have two inputs. You have output of the network and you have the ground truth. Okay. So, but that output of the network, it's actually coming from a chain of functions. But basically, if you just combine all of that, the basic input is your image. All right. So now if you have all those functions, so to be able to compute derivative for all those variables, you will have to make use of this chain rule. And this is again coming from your high school maths. So the simple chain rule says, if you have, let's say, this function L, and you want to compute derivative of this function with respect to any variable X, and the assumption is this function actually depends on this variable X. So if you want to compute this partial derivative, what you can do is you can compute the partial derivative of this function with respect to any other variable Z. Again, the function is dependent on this Z. And then you can compute the partial derivative of Z with respect to X. Okay, so this is the chain rule all of you must know. So this is just a recap. Now, if you try to think about the neural network, then if let's say X is like some variable inside your network, and then again, that variable is connected to Z, and then Z is actually connected to the loss function, right? So if you want to compute the derivative of like some kind of intermediate variable or your weight in your network, so you can actually make use of this chain rule. And again, this is just one step. Of course, you can go like deeper. You can have like multiple chains here because your networks will be like very deep. Okay. But however deep it is, mean you will still be able to find this partial derivative. And this is called like a simple chain rule. And this is what is used to compute the derivatives for like a loss function with respect to all the variables in your network. Okay, and this is actually used for backpropagation. So let's first try to understand what a backpropagation is. Let's say this is a very simple neural network. Okay, and we don't know like how many layers it has. It could be just one neuron. It could be multiple layers. But whatever it is, we can represent that in form of a function. Let's say the input to this is X and Y. So it will be a function. It will be a function taking X and Y as input, and it's producing an output Z. Okay, so this looks like maybe it could be a simple neuron, which is dependent on these two variables. Okay, so now if this Z is actually being used to compute the loss function, then what you can do is you can first compute the derivative of the loss function with respect to Z, which is easy because this Z will be like used in the loss formulation, right? You can just use derivative equations to compute that partial derivative. And once you have that, then the goal is to actually find partial derivative with respect to X and Y for the loss function, right? So then you can simply use this chain rule. So what you can do is you can first find the derivative with respect to Z, right? Which we can easily do here. And then in addition, you'll have to find the partial derivative of Z with respect to X. Okay, and again, we can do that because we have this function. We know what this function is. Now the idea is, if you remember like the gradient descent algorithm, you were finding that slope, and that was a loss curve, and the x-axis was different parameters, right? So what we do, we find that derivative with respect to all the parameters we have in our network. And since we can compute that using this chain rule, we can actually take that step, whatever like that gradient step we discussed, which was making use of the learning rate and the gradient. So that step is actually performed for all the parameters. And since you have the derivatives, you know the learning rate, you can easily update the weight value. Okay, so that's actually done for all the weights in all the layers. Okay, so that's how the network is being trained, and propagating these gradients backwards, like from the loss function all the way up to the input. This process is called backpropagation. Okay, this is also called like backward pass. And the other is like the forward pass, where you have the input, you use this function to get the output value. Okay, so that's the forward pass. And to compute, you first compute the derivatives. In fact, like the backward pass is something you actually update the values of the weights using the gradients which you have computed in this step. Okay, so when you train your network, these are the two things which is happening in each step. All right, so that was just one neuron. As I said, like your networks will be like deeper and deeper, but again, you can use the same chain rule. You can just expand those, and it's just showing that because you can compute the derivative for each variable here, right? Whatever variable you have for this layer, and then again you can just keep backpropagating by computing those partial derivatives. Okay, so some simple rules like which are used. So if you are actually adding two different values as a function, then what will happen? The gradient will distribute. So it will act as a gradient distributor, which means that whatever gradient is coming from the top, that will go equally to both the variables. If it's like if the operation is x plus y. Okay, and you can think about, because it's just a derivative, right? So if you compute derivative of x plus y, it doesn't matter. I mean, the derivative has to go to both. Okay, so that's one thing. And so if you have like the max operator, which you use for max pooling, right? So in this case, what will happen is it will act as a gradient router, because when you perform max pooling, only some of the values will be passed to the next layer, right? Others will be ignored. So if others are ignored, then it means those values are actually not influencing the output. So they're not dependent. So the gradient will be zero. So the gradient will not flow back in that direction. So whatever value was used for that max operation, gradient will just route in that direction. Okay, so it's a gradient router. And for multiplication, the gradient will switch. And again, this comes from like the simple gradient rule. If you have x times y, if you compute the partial derivative, if you compute partial, let's say you have an equation x times y, and you want to compute a derivative of L with respect to y. So then y will be just gone, right? Because it's just linear, and you will just have x. And that's why the gradient will switch. If it's y, it will go to x. And if it's coming from x, it will go to y. Okay, so just basic, don't worry too much about this. You won't have to like write any code or anything for this. These are just simple basics.